I'd like to do one more example from section 2.7, and we're going to crank it up a little bit further here and try something a little bit more abstract. We're going to work with higher dimension homogeneous coordinates. In order to do this, we're going to think of a copy of R3 three-dimensional space with points x, y, z sitting inside of R4 as the points with coordinates x, y, z 1 with a 1 in the fourth entry. So this is very analogous to imagining a copy of R2 sitting in R3. Here it's like a full copy of space sitting in this higher dimensional Euclidean space called R4. And we're going to do one exercise here together. We're going to find a 4x4 matrix that rotates points in R3 around the y-axis through an angle of negative 45 degrees, and then translates by the point 2, 1, 3 in R3. It's the translation that requires the use of homogeneous coordinates. We can actually talk about the rotation. I'm going to say here first the rotation in R3. We can talk about the rotation without homogeneous coordinates. So I'd like to do that first in R3, and then we'll shift to R4 for the second step. And it's a little bit trickier thinking about angles and rotation in 3D. Here's a diagram of XYZ space. You know, the way we decide the positive direction of angle measurement is, one way to think of it is with the right-hand rule. In the XY plane, if you point your thumb in the positive z-axis, your fingers then turn in the direction of positive rotation, which is counterclockwise in the XY plane. So if we're rotating around the y-axis, I want to point my thumb in the positive y direction, and then my fingers curve around in the direction of positive angle measure in the XZ plane. We actually measure positive angles from the z-axis to the x-axis in the XZ plane, which means negative angle measure would be rotation from the x to the z. So negative 45 degrees actually is an angle in that kind of position in the XZ plane. And if we imagine a curve of a unit circle, I'm going to label this point on the x-axis 1, 0, 0, so both y and z are 0. We're in the y equals 0 plane. This point on the z-axis is 0, 0, 1. And if I rotate 45 degrees in a negative direction, I end up at this point here. And without doing a lot of trigonometry, we know we're at this 45 degree diagonal. So the coordinates of that point are going to be, well, x and z are both positive. They're both going to be root 2 over 2, like the cosine and sine values of 45 degrees. And the y coordinate is still 0 there. And the 0, 0, 1 on the z-axis is going to rotate over to here, which is going to be a point where x is negative, z is positive, and because of this 45 degree angle, the x has to be negative square root of 2 over 2, y is 0 again, and z is still positive. Now, to describe this rotation in R3, I'm going to use that way we described in an earlier section of finding the standard matrix for linear transformation. If we can show what the E1, E2, and E3 vectors correspond to, so 1, 0, 0 is the E1 vector, through this rotation, 1, 0, 0 moves to the vector square root of 2 over 2, 0, square root of 2 over 2, right? That's just this point here moves to that location. The E2 vector, which is 0, 1, 0, is, doesn't appear in this picture of the XZ plane. It's actually one unit out on the y-axis, right? Here's 0, 1, 0. And because we're rotating around the y-axis, that just doesn't move. It stays put at 0, 1, 0. And the E3 vector, the 0, 0, 1, is up here, and it's going to rotate around to what we see as negative square root of 2 over 2, 0, square root of 2 over 2. And so it's easy now to write down the standard matrix of this linear transformation just using these three column vectors that correspond to the images of E1, E2, and E3. So square root of 2 over 2, 0, square root of 2 over 2, 0, 1, 0, and negative square root of 2 over 2, 0, square root of 2 over 2. So we're doing this rotation in the XZ plane, so notice it's like the first and third components that are affected. Now, if we only were doing a rotation in R3, that would be fine. But in order to compose with a translation, we need to shift to homogeneous coordinates in R4. So we're actually going to set up a 4 by 4 matrix working analogously to our previous examples, where we're going to put this 3 by 3 matrix in the upper left corner, in the lower right I have a 1 that sort of represents the idea that that fourth coordinate is just staying put. And then we need zeros across the bottom row and up and down the last column. And so there's our 4 by 4 matrix in R4 that represents the rotation. So that's one stage of this process. We also need to now consider the translation. So we're going to take x, y, z, 1 in this translation over to x plus 2, right? Y plus 1, z plus 3. And what we want to do again is think of a 4 by 4 matrix that we would multiply by x, y, z, 1 to get this x plus 2, y plus 1, z plus 3. Oh, I left something off here. We need that fourth coordinate that's going to stay 1. And again, you can think in terms of coefficient of x, coefficient of y, constant coefficient to help I'm sorry, coefficient of x, coefficient of y, coefficient of z, constant coefficient to help you fill in the matrix. That's like 1x plus 0y plus 0z plus 2 times 1 to get this first row 1, 0, 0, 2. Or you could also just think, what would I multiply across here with this column vector xyz1 to get the first entry? What entries would I need across the second row when I go through a matrix multiplication with the column vector to get the second entry here? So to get y plus 1, it's going to be 0x, 1y, 0z plus 1. And to get z plus 3, it's 0x, 0y, 1z plus 3. And the fourth row, we just want to get 1, so we want 0x, 0y plus 0z plus 1. So again, the idea is we're setting up a 4x4 matrix so that this product gives us the desired translation of that copy of R3 sitting in R4. So now we're not through yet, we're almost through. What we need to do is multiply matrices in order to compose these two actions, both the rotation and the translation. Rotation goes first. So this is the composition, transformation, and the operation that goes first, or the transformation that goes first, should be on the right. So I'm copying down my rotation oops, 0, 1, 0, 0, my rotation matrix from R4. Just recopying what we did moments ago, right at the bottom of my first page here. And then we're going to multiply by the translation matrix, which is right up above here, 1, 0, 0, 2, 0, 1, 0, 1, 0, 0, 1, 3, 0, 0, 0, 1. And the product of those two will give me our answer, right? The 4x4 matrix that would define this transformation of R3 sitting inside of R4. And when we go ahead and multiply across the first row, I gotta get square root of 2 over 2 in this position, across the first row, down here I get a 0, across the first row, down here I think I get a 0, across the first row, down the last column I get 2, and on with the matrix multiplication. My next row is 0, 1, 0, 1, square root of 2 over 2, 0, square root of 2 over 2, 3, whoops, I left something out here, sorry. This third entry going across the top should be negative square root of 2 over 2, right, because I'm doing the, to get that entry I'm going across the first row, third column. Yeah, that entry should be negative square root of 2 over 2. And then my last row is 0, 0, 0, 1, and there's our result. This is what we were after, this matrix, which if you can notice that when we do the rotation before the translation, it's easy to see the separate role of the rotation part of the matrix and the translation part. In that other example we looked at earlier, we did the translation before the rotation and things got all sort of complicated, right? So that's it. That's our last example for 2.7.